Today, we will be solving a RC op-amp circuit in S domain. For this circuit, we will be assuming there are no initial conditions. So our circuit contains two resistors in parallel, one 6K ohm and one 3K ohm. And these three resistors are in series with a 2K ohm resistor. Our input voltage is 24 UT volts, and we also have a 2 millifarad capacitor on the inverting loop of the op-amp. So before we begin, we first must draw the circuit in S domain by converting the resistors and capacitors into impedances. So when working in S domain, resistors are going to have the same impedance as when they were in time domain. So the resistor value should be the same. So for the first resistor, our impedance will be 6,000. For our second resistor, our impedance will be 3,000. And for our third resistor, our impedance will be 2,000. Our input voltage source, as it was 24 U of t volts in time domain, using a Laplace transform, this will turn into 24 over S volts in the S domain. For a capacitor, the impedance in S domain is 1 over the capacitor value times S, which in this case will make it 500 over S. And now our circuit has been converted into the S domain. So now that all the components are converted into impedances, we can begin solving for the output voltage. Before we do that, we must label the nodes of the circuit. So we already have Vout labeled, and we have two more nodes on this circuit, which will be Vn and Vi. So Vn is found on the non-inverting input of the op-amp, and Vi is on the inverting input of the op-amp. Due to the concept of there being no voltage difference between the input voltages of the op-amp, we know that Vn must equal to Vi. And due to the observing of the circuit, we can see that Vn is grounded, which means that it has a voltage of 0. And since Vi is equal to Vn, we know that Vi must also be equal to 0 volts. So now that we have our circuit in S domain and we have labeled our nodes, we can begin solving for the Vout. So before we start our nodal analysis, we can start off by finding the equivalent impedance of the three resistors found. So since we know that the 6K and the 3K impedance are in parallel, in S domain, we can treat them the same way as we would in time domain. So we're going to add them the same way that we would add resistors. So for the impedances in parallel, we will be using the formula of R2 times R1 over R1 plus R2, which in our case, using impedances, will be Z1 times Z2, divide that by Z1 plus Z2. And inputting our values, we get 6,000 times 3,000 divided by 6,000 plus 3,000. And we get an overall impedance for the impedances in parallel of 2,000. Now, knowing these two impedances are in series with the third resistor, we can just add this impedance that we found for the parallel ones and add that to the impedance of the third resistor. So we have 2,000 plus 2,000, and we get an overall impedance of 4,000 for these three resistors that are found. Now that we have found this overall impedance, we can begin to perform the nodal analysis, or KCL, at Vi to find V0. So we will first be taking the path of Vi to the input source. So we have Vi minus the input source, which we found that in S domain is 24 over S. So Vi minus 24 over S divided by the overall impedance that we just found of the 3 resistors, which is 4,000. Next, we will see the next path, which is VI to V out. So we will have VI minus V out, divide that by the impedance that we found for our capacitor, which was found to be 500 over S. And we know that all of this will be equal to 0. So using the observation that we found above, that BN is equal to VI, which is equal to 0, we can go ahead and cross out VI in our calculation, as we know it is equal to 0. And this further simplifies our equation down to negative 24 over S over 4,000 minus B naught over 500 over S. This is all still equal to 0. After that, we can further simplify it to get negative 0.006 over S minus V naught times S over 500 is equal to 0. Now we can move over this first component over to the right side of the equation in order to try to get V out by itself, which gives us negative V out S over 500 is equal to positive 0.006 over S. And we can further simplify this by moving the negative S over 500 to the right side of the equation by multiplying the inverse of it, which will give us V out is equal to positive 0.006 over S times negative 500 over S. And we can further simplify this to get that V out is equal to negative 3 over S squared. And this is our final answer for V out in the S domain. But if you recall, at the beginning, we are told to find V out of T for T is greater than 0. So now that we have our answer in S domain, we have to convert it back into time domain, which this will be done by using the Laplace transform. And using the respective Laplace transform, we find that V out of T is equal to negative 3T U of T, where T is greater than 0. And this is our final answer for V out of T for this op-amp circuit that was being solved in S domain.